Alright, what's up guys? So as you can see, today I'm back again with another video on past examination question paper, and now today I'm going to show you exactly how you're going to apply what you have learned in the previous video on the photoelectric effect. So this question is saying that in the diagram below, green and blue light are successively shown on a metal surface. In each case, electrons are ejected from the surface, right? So obviously one thing that you should know from this statement is that if electrons were ejected from the surfaces in both cases, that means the energy of the photons in green light and blue light, both of them actually are greater than the wake function of this metal here. So we should take note of that. And then now they say question 3.1.1, what property of light is illustrated by the photoelectric effect? Obviously, the photoelectric effect is there to demonstrate the particulate nature of light, or simply the particle nature of light. Right, moving on to question 3.12, right, they say, without any calculation, give a reason why maximum kinetic energy of an ejected electron using the blue light, right, the blue light is greater than obtained using the green light for the same metal surface. So in other words, they're saying EK here and the EK there, if we are going to compare them, this one is going to be greater than that one, right? Why is that? So here the main thing that you have to look at are the wavelengths that we have been given. This will give us the energy of the photon, remember, and since it's the same metal here, metal M and metal M, that means they have the same wake function. And if they do have the same wake function, that simply means they're going to actually need the same amount of energy. And what's going to determine the kinetic energy of the electron will be the energy that is going to be left after some of the energy have been used for their wake function. So in this case, we can think of it like this: energy of a photon is equal to hc over lambda, right? So you can see the energy of the photon is inversely proportional to the wavelength. So the larger the wavelength, the smaller the energy of the photon. Hence, that means the energy of the photon for the blue light, since it's smaller than the one for the green light, that means the energy for the photon for the blue light is going to be greater than the energy for the green light. Hence, we are obviously going to have greater amount of kinetic energy for the blue light. Remember, energy of a photon is also equal to the wake function plus the kinetic energy, which implies that kinetic energy of the photoelectron will be equal to the energy of the photon minus the wake function. So as you can see from this equation here, if we've got a larger energy of the photon, which we are going to have from the blue light because wavelength is inversely proportional to the energy of the photon, that simply means that at the end of the day, we are going to be left with more kinetic energy as compared to in green light, where this energy of the photon is actually smaller. So in other words, the kinetic energy for the blue light is going to be greater than the kinetic energy for the green light, because the wavelength for the blue light is smaller than the wavelength for green light, which implies that the energy of the photons for the blue light will be greater than the energy for the photons for the green light. Right, moving on to the next question, they're saying 3.2, the wavelength associated with the cutoff frequency. So remember the cutoff frequency or the threshold frequency is our F naught, the minimum amount of frequency required to eject electrons from a metal surface. The wake function of the metal, we should calculate the wake function of the metal, right? So to calculate the wake function of the metal, energy is equal to hc over lambda, because we are given the wavelength here, so we're going to use this equation, because this one would need the frequency if we were to use this one. So we're not going to use this one because we are given the wavelength. However, you know the wake function is indicated by W naught, which is going to be equal to hc over lambda, which is the cutoff wavelength. So substituting in this equation, this will be equal to, the Planck's constant is 6.63 times 10 to the power of negative 34, and then the speed of light in a vacuum is 3 times 10 to the power of 8. All this divided by the wavelength, and you can see here the wavelength is given in nanometers. So to convert the nanometers into meters, we simply multiply by 10 to the power of 9. So it's going to be 330 times 10 to the power of -9 to convert. Now this is in meters. Then our answer here, we are going to get exactly 6.03 times 10 to the power of -19 joules. Remember, this is energy, right? Now let's move on to the next question. Okay, so they say calculate the maximum speed of an electron ejected from the surface of the metal when light of frequency is shown on the metal. So obviously here, as you can see, for 3.2.2, we've got a frequency equal to, this is the frequency of the light, right? Frequency of the light equal to 1.2 times 10 to the power of 15 hertz. And then what we want is the EK max, which is equal to the one that we want to find. So obviously what we need to do is use that equation. Energy of a photon is equal to the work function plus the kinetic energy, which is the maximum kinetic energy. So you can see we want the speed. However, we know that the maximum kinetic energy or kinetic energy is actually indicated by this equation. The EK is equal to half mv squared. So we can use this equation to calculate the speed there. So we're simply going to substitute our values here. Okay, let me first substitute. So energy of a photon, remember also we can get energy of a photon from HF. In other words, energy of a photon is also equal to HF. So we're going to substitute for HF here because we have the frequency of the light. So to find the energy of the photon from that frequency, we actually use this. So it's going to be HF is equal to the work function. We're going to leave it like this because we do have it, because it's still the same metal. Then plus half the mass. In this case, this will be the mass of the electron, because the electrons are the ones that are ejected, times the speed of, or the velocity of the electrons squared. Then we simply substitute our values in here. Substituting our values in there is going to be equal to, remember the Planck's constant is 6.63 times 10 to the power of -34. Then this is going to be times the frequency. The frequency is 1.2 times 10 to the power of 15. This will be equal to the work function. Remember, we calculated the work function here. It's 6.03 times 10 to the power of -19, then plus half times the mass of an electron. You get it from the formula sheet. The mass of an electron is actually 9.11 times 10 to the power of -31, and then of course times v squared. And if you make v the subject of formula and calculate, you're going to see that your final velocity is going to be actually equal to 6.5 times 10 to the power of 5 meters per second. That will be the speed of the photoelectron. Okay guys, I hope you enjoyed this. Please like and subscribe.